In 2 days, a dead 5-ton rocket slams into the moon and throws 800,000 pounds of rock across a blast footprint 183 kilometers wide. Debris moving at the speed of pistol rounds, with no air to slow it down. Nobody aimed it, nobody can stop it. And nobody official is even watching. Here's the terrifying part. Within a decade, there will be people living on that surface. By the end of this video, you'll understand why this week's harmless crash is the warning shot almost everyone is ignoring. The clock on this one is now measured in hours, at 34 minutes past 6 in the morning, Universal Time on Wednesday, August 5th, 2:34 in the morning Eastern, in the dark hours after Tuesday midnight. The dead upper stage of a SpaceX Falcon 9 rocket slams into the near side of the moon at 2.43 kilometers per second. That is about 5,400 miles per hour, the equivalent of Mach 7 here on Earth. The prediction is not vague. The current orbital solution pins the moment of impact to roughly half a second, and the location to a few hundred meters, 19.455 degrees north, 93.594 degrees west, near a crater named Einstein on the moon's western edge, as seen from your backyard. The object is the second stage of the Falcon 9 that launched 2 commercial lunar landers back in January of 2025. It is about 12 meters long and 4 meters wide, the size of a 5-story building, and it weighs somewhere between 3,900 and 4,900 kilograms. When it hits, it delivers around 14.5 billion joules of energy. That is the equivalent of 3 tons of TNT, or roughly 15,000 sticks of dynamite, detonating against the lunar surface in a single instant. The blast will excavate a crater somewhere between 17 and 30 meters across and throw approximately 1,100 tons of rock and soil, 800,000 pounds of the moon, outward in every direction. The collision itself is the endgame of an 18-month orbital coin flip. After the stage finished its job, it was left in a high, lopsided loop around Earth, coming as close as about 220,000 kilometers and swinging out to 510,000, circling once every 26 days. The moon orbits at 385,000 kilometers, squarely inside that loop. The two paths cross, and for a year and a half, the rocket and the moon kept missing each other at the crossing point. On Wednesday, they finally arrive, at the same place at the same time. This will be only the second predicted impact of human space junk on the moon in history, and the first ever on the near side, where telescopes on Earth can actually watch it happen. None of this is in doubt. The impact has been tracked for 11 months, refined through more than 1,000 telescope observations, and confirmed by orbital solutions that have converged to almost absurd precision. Wednesday morning, it happens. And here is the part of this story almost nobody is talking about. The reason this event is a curiosity instead of a catastrophe comes down to a single temporary fact. And that fact is about to expire. The rocket cannot be stopped, and it is worth being precise about why. The stage has been dead hardware since January of 2025. It has no propellant, no power, no working thruster, and no radio. There is no command anyone can send, no engine anyone can fire, no mission anyone can launch in 2 days. Its path is set by gravity and sunlight and nothing else, but the uncomfortable truth sits one level higher. Even if the stage could be steered, there is no one whose job it would be to steer it. No agency on Earth is responsible for tracking dead rockets in the space between Earth and the moon, let alone deflecting them. The United States military maintains a catalog of debris in low orbit so complete it includes gloves dropped by astronauts 60 years ago. At the moon's distance, that entire system is blind. Radar follows an inverse fourth power law. An object 400 times farther away returns a signal roughly 25.6 billion times weaker. Military radar simply does not see 5-ton objects at 400,000 kilometers. The only reason humanity knows this impact is coming at all is one contract astronomer named Bill Gray, who runs orbit computation software from his home and noticed in September of 2025 that an object logged incidentally by asteroid surveys was going to hit the moon, not a government office, not a space agency. One man processing data collected by accident, backed up by a community of amateur astronomers. As of late February, 1,053 observations of this stage had accumulated from 5 observatories, plus the surveys and the amateurs. That is the entire global tracking apparatus for objects like this one, and it gets worse when you look at what this impact would actually do to anyone standing nearby. The moon is empty. That is the complete list of reasons Wednesday's impact costs nothing. There is no property line inside the debris field, no habitat downrange, no astronaut on the surface, no infrastructure within 1,000 kilometers of the impact point. A 5-story building traveling at Mach 7 can strike an entire world without consequence, because that world currently has a population of 0. Now run the same event 15 years forward, and the physics stops being trivia and starts being a threat assessment. NASA, China, and their partners have published schedules that put human beings, habitats, power systems, and landing pads on the lunar surface, permanently, within roughly a decade. Every one of those schedules assumes the ground underneath is safe. Wednesday morning is a live demonstration of how safe it actually is. The numbers that follow are the ones every base planner should be staring at, because this rocket is about to publish them in real time. The crater is the least of it. A team of researchers at the University of Texas modeled the debris cloud this specific impact will produce, and their numbers, submitted to geophysical research letters in July, describe something closer to area bombardment than a hole in the ground. The ejecta curtain, the cone of rock and dust thrown up by the blast, rises 15 to 20 kilometers. A central spike of fine debris shoots 75 to 100 kilometers straight up, and the lateral spread reaches about 183 kilometers from the impact point. That is a debris footprint wider than the state of Connecticut, produced by a crater the size of a tennis court. The speed of that debris is what turns it lethal. Ejecta leaves an impact of this type at roughly 100 to 300 meters per second, and that range is not abstract. 100 meters per second is the muzzle velocity of a pistol round. 300 meters per second is approaching a rifle round. On Earth, air resistance strips energy from every fragment within seconds. The moon has no air. Every rock, every grain, every shard of aluminum leaves the crater on a pure ballistic arc and arrives at its landing point carrying essentially the same energy it left with. A pebble thrown 90 kilometers on the moon is still a bullet when it comes down. Keep the scale honest, because the honesty makes it worse. By lunar standards, this is a slow, small impactor. Natural meteoroids arrive at 10 to 70 kilometers per second, several times faster, and the stage is mostly hollow tankage, which is why the crater will be modest. 800,000 pounds of ejecta is still the payload of more than 200 loaded dump trucks, flung outward at firearm velocities in a fraction of a second. If the gentlest artificial impact the moon is likely to receive still produces a Connecticut-sized debris footprint, the planning number for everything faster and heavier only grows from here, and this is a small impact. Nature does far worse routinely. In the spring of 2024, a natural meteoroid gouged a crater 225 meters across into the lunar surface, roughly 10 times the diameter and 1,000 times the ejecta of Wednesday's event, and nobody on Earth noticed it happen in real time. The moon absorbed a city block scale detonation, unwatched. Every event in that class, natural or artificial, would be a mass casualty event at an inhabited site. The difference between the two is that the artificial ones are entirely self-inflicted, and the evidence of how far their damage reaches is already photographed. The danger does not stop at the surface. That modeled central spike, 75 to 100 kilometers of altitude, matters because of what flies through that region. NASA's Lunar Reconnaissance Orbiter, the spacecraft that has been mapping the moon since 2009, works in an orbit that dips as low as about 50 kilometers. Debris from a surface impact of this size is predicted to climb higher than an operational spacecraft's orbit. Nobody expects LRO to be struck on Wednesday. Space is forgiving that way, and the orbiter's track is known. But the principle now has a number attached. On the moon, a ground impact is also an orbital debris event. A future base does not just need to worry about what lands near it, everything parked above it is inside the blast envelope too. The surface record backs this up at scale. When the Lunar Reconnaissance Orbiter compared before and after photographs of the same terrain across 7 years, it found 222 brand new impact craters that had appeared during the survey. But the more important discovery was what surrounded them. Roughly 47,000 secondary disturbances, patches of churned surface the researchers called splotches, scattered up to tens of kilometers from the craters that caused them. Each splotch marks a spot where thrown debris came back down hard enough to rework the ground. 47,000 recorded strikes from flying rubble in 7 years on a surface humanity intends to build on. The shrapnel radius is not theoretical. It is photographed, cataloged, and enormous, and its effect on machinery has already been measured directly. The one time humanity got to inspect hardware that stood inside a lunar debris spray, the results were sobering, and the debris spray in question came from a landing, not an impact. In November of 1969, Apollo 12 touched down about 160 meters from Surveyor 3, a robotic probe that had been sitting on the moon for 2.5 years. The astronauts walked over, cut pieces off the probe, and brought them home. Analysis found the surfaces facing the lunar module had been sand-blasted, pitted and scoured by dust accelerated by nothing more violent than a descent engine, easing a spacecraft down at walking speed. Consider what current designs are actually built to withstand. Spacecraft and suit shielding for the lunar surface is engineered against micrometeoroids, grains and flecks, the sandpaper of space. It is not engineered against marble-sized and fist-sized rock arriving at pistol velocity, because armor against that would be too heavy to launch. The protection plan against larger debris has always been statistical. The moon is big, impacts are rare, the odds favor you. Wednesday's event quietly rewrites that calculation, because it adds a category of impactor whose arrival rate is not set by nature at all. It is set by launch cadence, and launch cadence is going up. A rocket engine plume is the gentlest debris event the moon has to offer. Wednesday's impact carries the energy of 3 tons of TNT and throws its debris at bullet velocities. Scale the Surveyor 3 damage up through that comparison, and the implication for a lunar base writes itself. Solar arrays are thin by design. Habitat walls are engineered to the gram because every kilogram costs a fortune to land. Spacesuits are fabric. An astronaut on the surface 90 kilometers from an impact like Wednesday's would be standing inside the documented debris footprint of pistol velocity fragments, with no atmosphere slowing anything down and no warning system in existence to tell them to take cover. That last part deserves emphasis. There is no impact warning network for the moon, no radar fence, no alert siren, no protocol. The only reason Wednesday's strike comes with 11 months of notice is that one man happened to check. An astronaut on the surface gets exactly as much warning as whoever is watching from Earth decides, on a volunteer basis, to send. The hardware precedent says even the survivable outcome is degraded equipment, and nobody gets to choose how far away the next impact happens, because as this rocket has spent 18 months proving, nobody chooses where these things come down at all. The impact point near Einstein crater was never selected. It emerged. When the June 8th orbital update came in, the predicted point jumped 170 kilometers to the northwest. The July 17th update moved it about 10 kilometers more. The stage is tumbling end over end, and sunlight itself, the faint push of solar radiation on a rotating body, has been steering it for a year and a half. That is what an uncontrolled arrival looks like. A 5-ton object whose destination wanders by more than the width of a metropolitan area between tracking updates, right up until the final days. Here is the coordinate that should get more attention than it has. The impact site sits at roughly 19.5 degrees north latitude. The lunar South Pole, where NASA intends to put its Artemis surface camp, and where China intends to build its research station, is about 2,700 kilometers away. Wednesday's debris will land nowhere near any future base site, but that outcome was not planned, negotiated, or protected. It is luck. A dead stage in a moon-crossing orbit can come down anywhere its path intersects the surface, and this one's path was being edited by sunlight until a few weeks ago. The next derelict, and there will be a next one, rolls the same dice over terrain that will not stay empty. The schedules that end the moon's emptiness are public, funded, and closer than most people think. The occupation timeline is no longer science fiction, and it is worth laying out plainly because it is the other half of Wednesday's story. In February of this year, NASA restructured the Artemis program. Artemis 3, targeted for 2027, will now fly a docking demonstration with the new commercial lunar landers, and Artemis 4, targeted for 2028, carries the crewed landing, the first boots on the moon since 1972. The architecture beyond that calls for a surface camp near the South Pole, built out mission by mission. China's schedule runs parallel and, if anything, more aggressively. The Chinese program has publicly committed to landing its own astronauts on the moon before 2030, using 2 launches of the Long March 10 rocket and a lander called Lanyu. Its robotic precursors are already flying. Chang'e 7 launches this year to survey the South Polar region, and Chang'e 8 follows around 2028 to test building materials made from lunar soil. Both feed into the International Lunar Research Station, a permanent base also at the South Pole with its first construction phase scheduled for completion by 2035. Notice what both programs have in common: the same destination. The South Pole is where the water is, ice locked in permanently shadowed craters that future crews intend to mine for drinking water, breathable oxygen, and rocket propellant. That resource logic means lunar settlement will not be spread thinly across a world with the surface area of Africa. It will be concentrated. Habitats, power systems, landing pads, and people clustered into a handful of prime sites within kilometers of each other. Concentration is efficient, and concentration is exactly what a 183-kilometer debris radius punishes. One bad arrival near the wrong crater rim does not threaten a base. It threatens the neighborhood that holds every base. Put the 2 programs together, and the picture is unambiguous. Within a decade, on published schedules, there will be crews, habitats, power plants, and landing infrastructure standing on the surface that Wednesday's rocket is about to hit for free. 2 spacefaring superpowers have chosen the same neighborhood at the same pole in the same decade. And every mission that builds those bases, every lander, every cargo run, every crew rotation, rides to the moon on a rocket that leaves a stage behind somewhere, which is exactly how the object hitting the moon this week came to exist, and why the traffic problem compounds instead of resolving. The supply line for lunar settlement and the supply line for lunar debris are the same supply line. The stage that hits the moon on Wednesday was not some anomaly of a careless era. It was launched in January of 2025 on a mission that successfully delivered a commercial lander to the surface. The delivery worked. The leftover is what is hitting the moon. More than 600 Falcon 9 rockets have flown, and most of their upper stages are disposed of responsibly, either burned up in Earth's atmosphere or thrown into orbit around the sun. But translunar missions leave their stages in exactly the kind of high, moon-crossing orbit this one occupied. And there are already roughly a dozen known derelicts drifting through that volume right now. Known? It bears repeating, because one contractor and some amateurs bothered to look. The honest number could be higher. Now project the traffic curve. Every crewed landing requires multiple heavy launches. The Artemis architecture needs tanker flights by the handful for a single surface mission, and China's plan uses 2 boosters per landing by design. NASA's commercial delivery program already buys several robotic lander missions per year, each riding its own rocket. Every one of those flights produces a spent stage that ends up somewhere, and the somewhere is chosen by the operator's convenience. The derelict population in moon-crossing space and the human population on the lunar surface are scheduled to grow through the same decade, on the same curve, fed by the same launches, while the tracking system remains one contractor and a mailing list of amateurs. What makes this maddening rather than merely worrying is that the fix already exists and costs almost nothing. Heliocentric disposal, using a few minutes of leftover propellant to throw a spent stage into orbit around the sun, where it can never return to hit anything, has been done repeatedly. It was done for the stage that launched the James Webb Space Telescope. It was done as recently as November for the Falcon 9 stage from a lunar science mission. It is a trajectory choice, not a technology, and no rule anywhere requires it. No treaty, no licensing condition, no agency mandate compels any operator in any country to dispose of a lunar-bound stage, to track it afterward, or even to report where it went. The 2022 precedent shows how far the blindness extends. The last time a piece of junk hit the moon, the world spent weeks misidentifying whose rocket it was. First blamed on SpaceX, then traced by independent observers to a Chinese stage, which China denies to this day. When the crater was finally photographed, it was inexplicably double, suggesting mass on the rocket that nobody has ever accounted for. Identity unknown, contents unknown, owner unaccountable. That is the current state of the art for objects arriving at a world we are about to inhabit. On Wednesday, the arrival at least comes with an audience. If you want to see the strike, the geometry favors this side of the planet. Observers across the eastern half of North America and much of South America will have the moon up in dark sky at the moment of impact. It rises around midnight to 1 in the morning, local time in the eastern United States on Tuesday night, with Saturn shining nearby. The flash itself is probably a lost cause. The sight is in daylight, and even NASA's deliberate impact experiment in 2009 produced no flash visible from Earth. The target is the dust. Because the strike lands almost exactly on the moon's visible edge, the debris plume may rise off the limb in silhouette against black sky. Telescope observers should run high frame rates, 20 per second or more, keep the moon's bright disk just off the edge of the sensor, and consider an infrared filter to cut the glare. Tonight, Monday, offers a dry run. The moon sits in nearly the same position, one night early, and the observing campaign recommends practicing on it. The most ambitious observers will hunt something never captured before. A narrow spectral line at 670.8 nanometers, the fingerprint of lithium from the stage's aluminum lithium tank glowing in the debris cloud, the first chemical signature of a human object written into a lunar impact. In the weeks after, the Lunar Reconnaissance Orbiter will photograph the fresh crater, and that picture will settle real science. A projectile of known mass, speed, and angle gives crater-scaling physics a calibration point that natural impacts never provide, the same physics used to plan asteroid deflection. Watch for the crater image, watch for whether it is single or double, and watch whether the plume observations match the models, because those answers set the injury radius for every impact scenario planners will run from now on. But the bigger thing to watch is institutional, and the window for it is short. Every argument in this story converges on one requirement. Before people live on the moon, someone has to be assigned to watch what is falling toward it, and disposal of lunar-bound stages has to become a rule instead of a courtesy. Both fixes are cheap. Tracking means funding work that one contractor currently does as a side project. Prevention means requiring a burn that operators already perform when they feel like it. The demonstration of Y lands Wednesday morning at 2:34 Eastern on a world that is only defenseless because, for a few more years, it is only empty. We will be tracking the impact, the plume, and the crater photo, and what happens after this one hits will tell you whether anyone in charge was watching.